Hello everyone, and thanks for listening to my talk. Today I'll be discussing some of the work I've done in collaboration with Professor Shirley Dyke and Professor Bilionis at the Resilient Extraterrestrial Habitats Institute. Our research focuses on physics-based model identification of experimental systems for the purpose of predictive modeling. We found that approaching this problem from a Bayesian perspective allows us to develop an appropriate framework to tackle issues like resilient design and decision-making in the built environment, whether that's on Earth or out in space. Bayesian inference is no small field, however, and the complex nature of the systems we're trying to learn about necessitates that we leverage a variety of proximate inference methods to develop an efficient and accurate representation of the experimental system. I broadly classify these approximations as analytical methods, sampling methods, and optimization methods. Analytical methods are perhaps the most ubiquitous in the identification of experimental structural systems, as they are most apt to sidestep the curse of dimensionality through the computational efficiency of an analytical solution to the Bayesian inference equations. These methods are constrained, however, in their representation of the posterior uncertainty, which can be problematic in the representation of highly nonlinear non-Gaussian systems. In contrast, sampling methods retain the most flexibility in their representation of the posterior, and are guaranteed to converge in expectation to the true posterior as the number of samples approaches infinity. However, the samples needed to achieve a reasonably accurate assertion of the posterior uncertainty grows exponentially as the dimensionality of the system increases, which can be a barrier to the practical implementation of these techniques. Optimization methods seek to strike a balance between the previous two techniques, thereby opening up possibilities for efficient and flexible inference in high-dimensional nonlinear systems. It is on these techniques that we have directed our focus for this work. In this study, we build on the theory of optimization methods for Bayesian inference to develop a novel approach to Bayesian filtering for the identification of complex structural systems. We evaluate our method using experimental observations from a nonlinear energy sink device, subject to base excitation, and compare our results to those of an unscented Kalman filter. The filtering approach we've developed is based on an optimization method known as automatic differentiation variational inference. The concept behind variational inference is actually quite simple. Since we don't know the exact form of the true posterior, shown here in orange, we take what we do know about the system and propose a flexible distribution that we think might be able to approximate the posterior, shown here by this dotted blue line. Our goal is then to get this approximation of the posterior as close as we can to the true posterior, which we achieve by carefully selecting a loss function, shown here on the right. The loss function typically selected for this class of problems is called the elbow, which is short for the evidence lower bound. Breaking it down component-wise, the elbow balances the fit of the posterior model to the observed data with the uncertainty associated with our prior knowledge, ideally giving a solution that is not overfit to the data used for training. With the loss function established, we then perform the optimization through stochastic gradient descent. Now, this is great if we are able to look at all the data at once. However, it is often desirable to update our beliefs about the system continuously as more data become available. We accomplish this within the variational inference framework by iteratively performing inference on small batches of data in the time history, where S is the length of the batch. We choose to incorporate the ability to overlap between batches to provide additional opportunities for the optimization of the posterior on the overlap section of data. For simplicity, I'm going to collect all of the samples in a particular batch and refer to them as B sub I. To infer the states and parameters of the system from the data available in each batch, we must move through the predictor-corrector paradigm implicit in Bayesian filtering. We accomplish this in two distinct steps. In the predictor phase, we move into the current batch by propagating a limited number of samples over the states and parameters forward from the approximate marginal posterior of the previous step. The approximate marginal posterior is then formed through automatic differentiation variational inference, which optimizes the approximate marginal prior toward the true posterior. Looking at each step in a little more detail will illuminate the operations of the filter. Let's start with the corrector step on batch B sub I minus 1. Here our goal is to bring our initial guess about the posterior distribution as close as we can to the true posterior. We do this by approximating the true posterior with a variational family, denoted by G. Our choice of variational family directly impacts the speed and accuracy of our inference. To balance these outcomes for relatively simple dynamical systems, we assume a variational family that expresses independence between the states and the parameters, and models each as Gaussian. Different assumptions on the variational family could be used to develop other behaviors in the posterior, such as multimodality or constrained parameter spaces, but we neglect these here for the systems that we're going to observe in this presentation. Once the variational family has been established, we then optimize it against our data to form an approximation of the marginal posterior. The approximate marginal posterior developed in the previous step can then be used as a basis to approximate the marginal prior for the current batch. The development of the marginal prior progresses differently between the parameters, which are assumed constant, and the states, which vary with time. In the case of the parameters, the approximate marginal posterior from the previous step directly informs our assumption of the approximate marginal prior. For the states, we use the approximate marginal posterior as a stepping stone to propagate the uncertainty in the states forward in time. We do this by developing a sampling approximation to the mean and covariance of the assumed marginal prior. We split this approximation into two parts. The first portion, which encompasses the states already inferred in the previous batch, is taken directly from the approximate marginal posterior, similar to the parameters. The second portion, which includes the states corresponding to the new observations, is developed by propagating samples from the approximate marginal posterior of the previous batch through the state equations. With this framework in place, we can apply the variational filter to an experimental system. The system we've applied this method to is known as a nonlinear energy sink. These devices extract and dissipate energy over a range of frequencies from the primary structure to which they are fixed, which makes them valuable for structural control. However, due to a distinct bifurcation in their behavior, they can be difficult to identify experimentally, making them an interesting case study. Our prototype device, shown on this slide, consists of a mass traveling on a glider rail, constrained in its motion by the action of a wire threaded through its center. The system is driven by an actuator simulating base excitation. The key component of the nonlinearity in this device is tied to the variations in stiffness caused by the geometric relationship between the moving mass and the fixed ends of the wire. Coupling that stiffness with an initial tension in the wire leads to this expression of the stiffness force. Assuming relatively small vibrations, about x equals 0, we can take the Taylor series expansion of this square root term, leading to a clean expression of the stiffness up to the third order, where the first term corresponds to the linear stiffness of the system, and the second term corresponds to a stiffness parameter influenced by the cube of the displacement. Experimental observation of the system also led us to include a friction damping term in the equation of motion, shown here with the hyperbolic tangent. With this understanding of the system, we can then proceed to infer the states and the parameters, which include viscous damping, friction damping, linear stiffness, and cubic stiffness. Our goal with the variational filter is to develop a method that provides a reliable interpretation of the posterior uncertainty regardless of reasonable variations in the assertion of the prior, which can shift depending on the person performing the inference. We therefore assess the effectiveness of our filter by first asserting 100 feasible priors on the states and the parameters. Those priors then allow us to develop 100 candidate models using both the unscented Kalman filter and the variational filter frameworks. We finally determine the best candidate models through a comparison of the true system observations with results simulated with respect to the mode of the posterior on the parameters. I show the best results here on this slide, where the blue lines give the observed response of the system and the orange lines show the simulated response of the best candidate model developed using the unscented Kalman filter identification, and the yellow lines show the simulated response of the best candidate model developed using the variational filter identification. What you should notice about these results is that both the UKF and VF models give approximately the same representation of the system behavior, which is quite similar to the true response of the system. The key difference in these results is the computational effort required to develop them. Though the variational filter is more efficient than the batch implementation of variational inference, it still operates on the order of hours, whereas the results of the UKF were generated in seconds. We can gain further insight by examining the remaining candidate models of the system. In these figures, I've plotted the distribution of candidate models with respect to each parameter for both the UKF and VF approaches, where the best model for each inference method is noted by the respective stars, orange being for variational inference and blue being for the unscented Kalman filter. The first thing to note here is that the best models, though they produce similar results, are built on very different sets of parameters. In part, this is due to slight differences in the construction of the posterior model, due to the assumptions used in the variational filter and unscented Kalman filters, respectively. However, the algorithms also have different means of searching through the space of the inverse problem, leading to different interpretations of the resulting posteriors. However, regardless of the differences in the best solution, the overall results do show a lot of similarity. The mode of the models aligns well with whatever that best solution is, and the confidence with which the stiffness parameters are inferred exceeds that for which the damping parameters are inferred, for both inference approaches. Final insights concerning these two approaches can be drawn by observing the respective root mean square errors of each of the proposed candidate models when evaluated against the response behavior used for training. As can be seen in these figures, the variational filter and the unscented Kalman filter results both show a similar spread of error and accuracy level, despite differences in the candidate models. These results indicate that both methods, with their various foundational assumptions, infer useful though imperfect models of the system, where the inference results achieved by any of the candidate models are similar to those of any other. Overall, this application of automatic differentiation variational filtering demonstrates several successes of the method and some remaining challenges that require further development. In this study, we have shown that the variational filter can be used to iteratively infer the states and parameters of continuous data streams, giving comparable results to established methods. However, we also found the computational load induced by the filter is still very high, rendering it ineffective for many practical identification scenarios. Furthermore, the selection of the variational family was also found to be quite nuanced, which may lead to difficulties in the broader application of this method. By addressing these challenges, we hope to develop a flexible and efficient alternative to the analytical and sampling approaches to Bayesian inference. I want to thank you all for listening to my talk today. Please feel free to send me any questions by email, which is listed here on this slide.